In this video, we're going to review the basics of probability. So this is going to help refresh your memory for some of you on how we define probability in terms of likelihoods of events. And for those of you who haven't taken a course in probability, some of this may be new, but the hope is not that you're going to be a master of probability by the end of the next video, but rather that you'll have a basic understanding and that some of the notation which you may encounter as you're doing research on your projects, or even as we're defining a couple of basic theorems, that notation won't necessarily catch you off guard. All right, so let's start with the definition. What do we mean when we say the probability that an event happens is P, say? So let's think about the example of a coin flip. When we say that the probability of flipping a coin and getting heads is 1/2, what do we mean? Well, the way that we define probability is that we need to think about the likelihood or the frequency of an event occurring in repeated experiments. So the way that we would say determine experimentally that the probability of a coin flip being heads is 1/2 is we would flip a coin over and over and over again. We would count up how many times heads came up and then divide that by the total number of experiments. So if you look at this formula over here, on the left side, we see the numerator is the frequency of the event that we're trying to compute the probability of. So you can think of A as being coin comes up heads, and Fn is the number of times that occurred. If we divide that by the number of experiments n, and let n go to infinity, meaning we have to do many, many, many experiments, one would not suffice, then that ratio should approach some constant, and whatever that number is, we will call the probability. Okay? Now, there are a couple of things we can say about this answer. Because the frequency is obviously somewhere between 0 and n, the probability of the event has got to be some number between 0 and 1. And if we get a probability of 1, that means that it happened every time. And so an event with probability 1 would be certain. It's going to happen 100% of the time. And an event that occurs 0 times, we would call improbable. So probability of 0 means the event is improbable. Now, you may be a little bit surprised by that terminology. Why don't we call it impossible? Well, think about a guessing game where I say, I'm thinking of a number between 1 and 10. Now, if I ask you to guess that number, you're probably going to guess an integer, right? 1, 2, 3. But I didn't necessarily say that the number I was thinking of was an integer. So if we play this game so that the choices are allowed to be something like the real numbers, well, then the probability that you guess the answer is going to be incredibly small. In fact, well, there are infinitely many numbers between 1 and 10, if you take into account real numbers rather than just integers. And so any given one that I pick, the probability that you pick exactly that one would be 0. Now, is it impossible that you could guess the right number? Well, no, of course not. You just have to guess it. But the likelihood of that is so small that the probability is 0, meaning it doesn't really matter how many times we run our experiment, it's not going to happen. And so we would call that event improbable. All right, last thing I'll mention here is that probability is a forward-looking notion. If we talk about a coin that was flipped yesterday, it doesn't really make sense to talk about the probability that it came up heads or tails. Since it already happened, it either was heads or it was tails. We may not know the answer, but the probability is either 1 or 0 because the outcome is certain. All right, so probability only makes sense when we're talking about events that haven't happened yet. Otherwise, the probability is just 1 or 0. Now, this definition and that last property comes from a school of thought called the frequentist school. There are other definitions of probability or probabilistic type concepts called Bayesian probabilities, and those have a slightly different definition. They're very useful in applied math, but they're outside the scope of what we're going to talk about in this class. So I just want you to be aware that if you do see another definition of probability down the road, it may differ from this one slightly because this is a frequentist definition, and that's what we'll stick with in math modeling. All right, so let's introduce some of the notation and a few of the basic properties of probability. The first is that often we're going to be interested in an event where we're basically picking a random variable. So let's use capital letters to denote random variables. So capital X would denote a random variable, and lowercase letters to denote the outcomes of an experiment. So if you see something written like PR for probability, that capital X equals little x, it's saying what's the probability that our random variable, big X, takes on the value little x. Now, we can talk about single events, but often we're going to be interested in situations where there are multiple random events happening simultaneously. And if we want to talk about the probability that two events both happen, then we can define what's called a joint probability. And for joint probability, we'll just list off all the different events separated by commas. So the probability that big X is equal to little x and big Y equals little y is the joint probability of those events occurring. And you can relate the probabilities of individual occurrences to the joint probability using a summation formula. And so if you basically account for every possible value of y and add up the joint probabilities that x takes on the value little x and y takes on every other outcome, then you'll end up with a probability just for x, big X being little x. Okay, so that's the total probability rule. On the next slide, the next bullet point, we have what's called conditional probability. And this takes into account the fact that sometimes two events can be related. Sometimes knowing what happened as a result of one experiment can tell you something about another experiment. So for example, if you are rolling dice and someone then tells you that the number that came up was greater than 3, well, that tells you something about whether it's likely to be even or odd. You know a little more information that, well, the numbers greater than 3 rather, are 4, 5, and 6. Two of them are even, and so you can be more confident that the outcome is going to be an even number than if you just have a generic dice roll. So conditional probability says the probability that x is a given value little x, given some information about another event y, and we use a vertical bar to denote that. So the thing after the bar is the information that we're given, and the thing before the bar is the probability that we're trying to estimate. And you can relate joint and conditional rules for probability using this formula here at the bottom. It says that the probability that big X equals little x and big Y equals little y is the conditional probability that big X equals little x given Y equals little y times the probability that big Y equals little y. So I'll write that. It got cut off from the slide a little bit. I'll rewrite that. So again, the joint probability is the conditional probability of x given y times the probability of y happening. Okay? All right. Now, the reason that we define those terms, and in particular conditional probability, is that the type of model we're going to look at soon is called a Markov chain. And what we'll see is the fundamental definition of a Markov chain involves conditional probability. Okay? So what is a Markov chain? A Markov chain is a process that has two properties. The first is that there are a finite number of different outcomes called states. And so an example of this would be our rental car model. If you think about cars, they can either be in two locations, Orlando and Tampa. And so in that case, we would have just two states, cars in Orlando, cars in Tampa. And if you think about many cars, then the number of states would be much larger, because you could think about Orlando could have 0, 1, 2, 3, or any number of cars, and the same thing with Tampa. But as long as there's a finite number, then we might be able to use a Markov chain. And then the other property that they must have is that the probability of transitioning from one state to another state is given by the following formula. The probability that the next state is little xn, given all of the history, is the same as the probability that the next state equals xn given the previous one. In other words, if I want to know where I'm going to end up tomorrow, all I have to know is where I am today. What happened the days before that are irrelevant, and assuming that the interval of time here is a day. In other words, Markov chains are memoryless random processes. It doesn't matter where you were in the past, it just matters where you are now when you want to determine where you're going to go next. Okay, so we'll look into some of the mathematical details of Markov chains in the next video.